Fellow members and more, welcome to AI Toronto's first meetup of 2019. I am Hiren Dosani, your host for today's evening. And today evening is special for multiple reasons. The first being all of you. All of you RSVP'd and you made it. Trust me, somehow it's not an easy thing to do. I truly appreciate dedication of all of you. And I promise you that tonight it won't be wasted. Because you know what? We have two ace speakers. They are expert in their respective subject areas. And I'm highly thankful to them for sparing time for all of us here. To begin with, somebody asked me, hey, how do you handle 1 billion records on a daily basis? Now, I dealing with streaming architecture, I was like, I don't know. Maybe Jaspreet knows. And I definitely know that she knows that. And to introduce Jaspreet briefly, she did her master's in computer science and currently working as a data scientist in an AI-based company in Toronto. And she deals with terabytes or exabytes of data on a daily basis. To know more about what she does at work, to predict ad inventory, let's welcome Jaspreet.
Thank you so much. Hi, everyone. I'm Jaspreet. I have a master's in computer science from Ryerson. I'm a data scientist at Pelmorex Corp. And on a daily basis, I primarily work on PySpark and other big data technologies. And today, I will be talking about predicting ad inventory. All right, so about us. What do we do? Pelmorex, more popularly known as the Weather Network, is a weather, data, and advertising company, and I primarily work on the advertising side of things. I'll begin with briefly talking about what is ad tech and what is real-time bidding. The talk primarily focuses on defining the business problem, and we'll talk about the steps that I took to solve this business problem from development to deployment. I'll shed light on our tech stack and the data that we deal with on a daily basis. I'll also talk about this project's architecture. And finally, I'll discuss challenges and limitations. Okay, what is ad tech? Ad tech encompasses of all of the technologies used to display ads on your device as soon as you open an app. So it's a piece of software that is responsible for ad buying and placing, and this usually happens through ad auctions. These auctions allow multiple advertisers to compete for an ad space, and it allows for websites and apps to get paid more for each space. The ad buying process is done through algorithms and a distributed infrastructure that makes all the decisions. And the department that I work at is specialized in mobile in-app advertising. That is all the apps that you use on your phone and the ads that you see on your mobile phones. Basically, we deal with that. Okay, so what is real-time bidding? This diagram shows you an overview of what real-time bidding is. And I'll talk more about it in detail in the next slide. Let's just define some terms like an exchange, a demand-side platform. So real-time bidding is a predominant way of ad buying and placing. When a user opens an app, the app fires a bid request to an ad exchange. An ad exchange is a broker between app publisher, who is selling the ad space, and ad tech companies like us, who want to buy the ad space. And ad tech companies are also known as DSP, or demand-side platforms. Okay, so let's look at the detailed diagram for real-time bidding. So when a user opens the app fires a bid request to the exchange. When the exchange receives the ad request from your mobile app, it starts an auction, broadcasts the auction request to multiple DSPs. After receiving this auction request, the DSP evaluates this request to decide whether to bid on it or not using some complex internal processes. If we decide to bid on it, we respond to the exchange with a bid price and other ad parameters like the ad itself. The exchange then processes the responses received from the DSPs, decides the winning bid, and then displays the winning ad on the app. The DSP that won gets a notification that their ad was delivered to the phone. And this entire process takes about 200 to 300 milliseconds. So this is real-time bidding in detail. So that was the overview, and let's define some terms necessary to define the business problem that we are trying to solve today. A bid request is a request received from the exchange to display an ad. An impression is when that ad is displayed on your phone. Inventory is the number of available impressions. User profile is information or behavior extracted and saved for a user like age or gender. And finally, targeted advertising is displaying ads to a specific audience using user profile. For example, I have a business and I make tomato paste. And if I want to display this ad to multiple users, I'll go to a company like ours and ask them to do that. So in this case, targeted advertising is displaying these ads to all the genders, to people in Toronto, Ottawa, and Montreal. So this is targeted advertising in a nutshell. Now that we have a basic understanding of what targeted advertising is, let's define the business problem. Before displaying the tomato paste ad, the client will come up with various business rules. Example of business rules could be display this ad 50,000 times to all the genders aged 18 or more in Ontario and Quebec from Jan 24th to Feb 24th. 50,000 in this case is our expected total number of impressions or inventory, and the business rules are also known as targeting criteria. So before our team goes ahead and sets this ad up, we want to make sure that the impression number requested by the client is achievable, and to do so, we came up with this feature that is predicting ad inventory, which is the topic of our presentation today. So let's now define the business problem more formally. Given a targeting criteria, before setting up an in-app ad, predict the total inventory that an ad can achieve. Before getting into the details about solving the business problem, let's take a look at our tech stack. My team mostly uses Spark to build data products, and we primarily use Python. So it made sense to use PySpark for this project. We are reading several data sources from HDFS, Aerospike, ScyllaDB, and some CSV local files, and we are writing the output data to Elasticsearch. MongoDB is just used for saving configuration information that other teams are supposed to use, like the Elasticsearch server address, Elasticsearch index name, alias name, data field names, types, and so on. In this project, or the feature where we are predicting ad inventory, we are processing 4 different data sources to prepare our output data. The biggest data source that we process is bid requests. We receive about 4 terabytes of bid requests every day, which are stored in HDFS in the Parquet format. Parquet is an optimized columnar format, making reading this data in Spark extremely fast, like about a minute or 2. We process 2 terabytes of user profiles stored in Aerospike in dictionary-like objects. App categories are just categories of apps like sports, health, education, and so on. So it is one of the targeting criteria that we use. For example, if we want to target a user interested in apps that are health-focused, so we use that as a targeting criteria. App categories reside in ScyllaDB, and they follow a strict schema. We have about 400 MB of this data that we are reading from ScyllaDB. We process a local file to extract app information like app click-through rate, and it's a small CSV file. Let's not get into what click-through rate is. Maybe you can ask me about it later. This process data is about 100 gigabytes stored in Elasticsearch in dictionary-like objects. So this is the kind of data that we are dealing for this project. Let's look at the high-level architecture of my system. The Spark job is the main tool used to read, process, and write data. It reads data from several sources, processes them, and writes the output to Elasticsearch. Elasticsearch is the backend powering EngageFront. EngageFront is our front-end tool where we set ads and where our inventory predictor feature resides. You might be wondering, why are we reading from both Aerospike and ScyllaDB? We primarily used Aerospike to store our user profiles, but Aerospike is being used for several other applications and not just storing user profiles, so it started to grow really big, and maintaining it became really hard. So we decided to use ScyllaDB primarily for storing user profiles and to perform analytics, since it is faster and analytics is a lot easier to do on ScyllaDB versus Aerospike, as we can directly use SQL on ScyllaDB and we cannot on Aerospike. So we are in the process of using only ScyllaDB to read our user profile in this project and reduce the read data sources, thus making the system more simple. Okay, now let's get into the development steps. These are the basic standard steps I think most of the companies that we use. So I follow these basic steps while developing a feature. I usually start with analyzing the data, prepare it, and implement the code for the feature. I test the code on dev environment, and once everything is fine, I productionize it and test it on the production environment. I then deploy the system after the tests run smooth. Then comes the hard part, monitoring and maintaining the system throughout its lifetime. All these steps are usually repeated when I add new features to the system. Now let's take a deeper look at these systems, at these steps, one by one. Preparing the data for inventory predictor is a 4-step process. Cleaning entails basic steps like removing nulls, invalid strings, and converting the data into appropriate data types, and so on. And this applies to both input and output data. Transform involves machine learning, but more on this later. Merge basically combines the extracted user behavior from Aerospike with the predicted inventory that was outputted from the transform step. And finally, this data is aggregated. Now, aggregate is a very heavy process that computes unique number of users and total inventory for every possible targeting criteria that we can have in the ad setup. This involves exploring user behavior, group bys, and counting uniques and summing up the inventory for every possible targeting criteria. And all of this is done in Spark. Now let's take a closer look at the transform and the merge steps, the middle two. Okay. Transforming data. In this step, we want to predict impressions from bid requests. Remember, impressions are wins that the ads were actually displayed on the device. So those are impressions, and bid request is when we receive a request from the exchange to display that ad. Now, an inventory is just total impressions. Now, the system uses a simple classification technique to classify a bid request to win or no win. The wins are, once we classify the bid request to wins or no wins, the wins are saved, which are then fed to the merge process later. Our prediction module uses standard machine learning libraries found in the Spark documentation. This process is very simple. We start with preparing training data. The training data used is historical impression and placed bid data for the same day. This way we know that which bid requests were placed, and out of those placed, which one. So the one requests make our label like 1, and the one that didn't is the label 0, thus making it a classification problem. So this is how we found out our labels, which in our case is win or no win. And there is an imbalance in our data. We have more losses than wins. So we try to make the labels more balanced by inflating the impression data with new stochastic bid prices generated from the winning bid price. So think about it like if you have a winning bid price and now you want to make this data more balanced, that is increase the wins. So the winning bid price, you just create a random bid price that starts from the winning bid price to some kind of threshold that we decide. We never bid above that threshold. Because if, let's say that the bid price that won was $2, but if you bid using $5 was definitely win because the 2 was lowest one. So anything above it will definitely win. Sorry. Our feature engineering process follows the standard process of using string indexers, one hot encoders for categorical data, and then we just assemble these generated vectors with numerical data. We then train the model with this data and measure the performance using area under ROC curve and accuracy matrix, also found in the standard Spark libraries. The trained model is then saved to HDFS and is then served to transform bid requests into impressions. Okay, model evolution. So there are certain questions that you might have is how often do we train? We train only once a week, and the performance of the model is monitored manually for now, but we can add alerts to inform us if the performance drops in the future. The feature engineered pipeline and the new models are saved to HDFS with the current date. Now, why are we saving these models to HDFS? Because the data that we want to transform resides in HDFS. So I think it's better to read both these sources from Spark through HDFS. We could have investigated into using advanced ways of evolving our models, but we wanted to keep things simple, and this kind of worked out for us because our system was pretty simple. Okay, now merging data. We have predicted impressions, but now we need user behavior, as pointed out earlier, for targeted advertising. In the merge process, we join predicted impressions with user profile and app data. One of the most interesting issues that I personally have encountered when using Spark was handling data skews. The joins fail when there is a skew in data with memory issues, and no matter how much memory you give to your job, the joins will only fail faster. So it made no sense to keep giving more and more memory for these joins. So think about it as this GIF here. You're trying to put all that water in a cup, but the cup is not big enough to hold all that water. So a similar thing happens in Spark joins. When you join two data sources and you're using a key, that key needs to reside in one partition, let's say of your data frame. So if that data is larger than your partition, the join will fail. And this is one of the biggest issues that Spark cannot automatically handle, and we gotta handle this manually for now. So what did we do to mitigate this? Initially, I spent a lot of time trying to resolve this issue, and I found out that the device IDs that is being used to join impressions and user profiles, we had a lot of empty and null strings. So that's why cleaning the process is really important. We made a business rule that we don't want to count this as an inventory, so we decided to discard them. So the issue was fixed. But since we are reading the data from many different sources, generating that data, those systems could be buggy, and they eventually produce skew in the data. So now this we never accounted for in the beginning of when I was developing this. And then we found out that for one user, the user profile could grow pretty big, and we had no way of resolving it. I found out that we had very extreme cases. We had only 2 or 3 users, which does not really affect our inventory that much. So I decided to simply discard them. There are ways and more better ways of dealing with data skews. You can look them up, or you can talk to me about this later. Okay, Now, why did we decide to do this process offline? Why don't we just use our trained model and serve it in real time? So the prediction needs to be present to the customers in seconds. That's one of the biggest business rule that we have. Transforming bid requests, that is applying the trained model to the bid requests, took a couple of hours. Making user data available for targeting also take hours. Aggregating the available inventory also takes hours. So we just couldn't have done this in real time, and we decided to do all this process in offline and make all the possible predictions for all the possible targeting criteria in an offline process where the user can just use like an SQL statement and return the results instantly. So let me actually go back there and talk about, so this data is saved in Elasticsearch, all the merged impressions and predicted impressions and so on. And Elasticsearch is really fast when you want to aggregate data. So yeah, that's it. Testing. We decided to do manual testing, and we did a lot of unit tests for the methods and functions that we created. Now, testing is easier and could easily be automated if your results are deterministic, right? Because if you want to convert an age, raw age, to a bracket, the results will never change. But what about using a classification system where your results could be different every time you apply that model to? So our results were non-deterministic, and what we ended up doing was we used the results and we compared it with the actual ads that we set up and how much inventory did that ad deliver. So we kind of we used these methods to perform testing. And we also compared our inventory with a business analytical tool that gives us how many impressions were delivered, how many uniques for this ad, and so on. So we used manual testing for now. We couldn't automate it. And if you have some opinions and suggestions, I'm all ears. Okay. Check our blog out. We talk in detail about how we have used productionize our Spark jobs. And it's a great blog, and it talks a lot about HDFS logging and setting up server density alerts and using a specific directory structure. We always use that. Read it, it's great. And yeah, we tested the job on production, and we just deploy it and just schedule it on cron. Okay. Maintenance, just monitor everything. It is all automatic for now. We get alerts. So if there's a data skew issue or anything, we get alerts about these. And whenever we want to add new features, we repeat the entire process that I discussed. So you want to know how this feature looks like in Engage Front? So this is how it is. So you can see that at the end, this is what my job produces, impressions and unique users. We can ignore CTR for now. It's a very technical term. You can ask me later if you want. And the top part just gives a summary of how the ad was set up and what targeting criteria were used. And we get these results like in seconds. So challenges and limitations. One of the biggest challenges that I encountered was limited hardware. Although our Spark cluster is huge, we have 20 nodes, we are not able to do advanced machine learning like neural networks. Even something like decision trees takes forever. Adding more data and more features is also painful. When I started this job out, it took a day to run, but now after adding 2 features, it takes about 3 days. So that's one of the biggest limitations and challenges of this product. Aggregations become really hard to do when your data size grows, right? And we're producing 100 gigabytes of output data, and we are processing terabytes of data, so this is a big challenge. Like I said, testing probabilistic or non-deterministic data is a challenge, and we don't have automated processes for this yet. And there is a trade-off between accuracy and performance. Like I said, when we wanted to remove the data skew issue, I just discarded some users or devices. So there could be some issues in performance. So this is it. This was my first project at my company, and we've been working on it for about 2 years now. And yeah, any questions? I'm all ears. Thank you.